Dear student, today I am going to deliver a talk on group theory which is prepared according to the syllabus of Netaji Open University of PGMT paper 1A. In this paper, just we will discuss about some introductory part of group theory. First, we will discuss about some history of group theory, and then we will go for some definition of group, and then we will go for the definition of subgroup and then normal subgroups and some cosets. This is the total talk of this lecture. Okay, so to discuss what is a group, okay, to answer these questions we have to answer the following question. What is the symmetry? A symmetry of a geometric figure is an rearrangement of the figure preserving the arrangement of its sides and vertices as well as its distance and angle. Here this picture is an ammonia picture, the molecule of an ammonia. Here this nitrogen molecule and there is 3 hydrogen molecule. This molecule is a rotational symmetry. If we rotate this molecule with respect to the axis, then we can see this structure of this molecule remains symmetric, the same. Okay. So basically in group theory we studied this kind of symmetry of an object. Now we will see a symmetry of a triangle. In the first picture there is a triangle. This triangle is named as ABC, and if we do nothing, okay, then this triangle remains same. It will be named ABC. So here we are doing nothing. So here's the point of this triangle remains same. This is a one kind of symmetry. Okay. In the next picture, this triangle is rotated of 120 degree. Then for this rotations, the point of the vertices changes. Here A goes to B, B goes to C, and C goes to A. So this is a one kind of symmetry. In this picture, the structure of this triangle remains same, but only the vertices changes. We rotate this triangle of 240 degree, and for this rotation, the vertices changes A to C, B to A, and C to B. So this is a one kind of symmetry. In the fourth picture, the triangle is rotated with respect to an axis. The axis goes through the vertex A and meet the BC line perpendicularly. So for that reflection, the vertices changes. A remains same, A to A, but B goes to at the point C and C goes to at the point B. And in the fifth picture, we just reflect this triangle with respect to the line. The line goes through the point B and meet the line AC perpendicularly. Okay, and for that reflections, the point changes, that's the vertices changes, A to C, B to B, and C to A. In the last picture, in the sixth pictures, we reflect the triangle with respect to the line that passes through the point C and meet AB perpendicularly. And for that reflections, the vertices changes A to B, B to A, and C remains invariant. So for the triangle we get 6 kind of symmetries. Now for the square we have 8 kind of symmetries. The first picture, we just does not rotate this picture. This picture remains same. So we can say that we rotate this square just 0 degree. So it remains same. And in the second picture, we rotate this square of 90 degree. So here we get another kind of symmetry, and some name of the vertices changes. And similarly, we get just we have done 180 rotation or just 270 rotation, and later we just flip the square with respect to the line that passes the middle of the square. Okay, and in the later pictures we rotate or we flip the square through the line just that go vertically, and the last two picture we flip the square with respect to the line this is along the diagonal side. So in this picture we can see that the square has 8 kind of symmetry. So we listed the 8 kind of symmetry here. These symmetries we say that these are R0, R90, R180, R270, H, B, D and D dash. Here H and B are the symmetry where the square is flipped through the line that is vertically and horizontally, and D and D dash is the symmetry of the square when we flip the square with respect to the line that is diagonal to the square. So these 8 elements have some special property. What is the property? This property is if we combine any 2 elements of the 8 symmetries, okay, then we get a new element of this list. We will not get any other element but the element from the list only. For example, if we combine R90 with H, then we get D. Now this set of element is called dihedral group of a square and is denoted by D4. Similarly, we can define the dihedral group of Dn, which is the symmetry of a regular n-gon, and it contains 2n number of elements. The dihedral group arises frequently in arts and nature. Many of the decorative designs used on floor covering, pottery and buildings have one of this dihedral group as a group of symmetry. Chemists classify molecules according to their symmetries. Moreover, symmetries consideration are applied in orbital calculation, in determining energy level of atoms and molecules, and in the study of molecular vibration. Now there is this 8 picture where we can see that 8 picture has this special kind of symmetry. It's a rotational symmetry. If we rotate this picture in some specific angle, then we can see that this picture has the symmetry. So here we can define the group of these symmetries in this picture. Now let us consider another example. If we take a finite set A that has 3 elements 1, 2 and 3. Now consider the set symmetry of A. It contains all the bijection of A. Now if we take 2 bijection F1 and F2 of the symmetry of A, then and suppose the F1 look like that F1 of 1, F1 takes 1 to 2, F1 takes 2 to 3 and and also F1 takes 3 to 1. Then we can denote this F1 bijective map in a cyclic notation. So it can be expressed as a cyclic notation, this one 1, 2, 3. And if we take another bijection which is F2, and if F2 takes 1 to 1 and 2 to 3 and 3 to 2, then we can express this F2 as a cyclic notation of 2, 3 in this order of here 2, 3. Here we omit 1 because here 1 goes to 1, so that's why we just omit 1. Here each element of this symmetry of A is called permutation of A. Now the element of symmetry of A are the following in cyclic notation. Here E is equal to identity. It basically the identity element, when it applies on the set A, then it takes 1 to 1, 2 to 2 and 3 to 3. So that's why we have denoted it identity element. Now it's A1 is 1 to 2 and it takes 3 to 3. So that's why we omit 3. So we just simply denote A1 by 1, 2 in a cyclic notation. A2 is denoted by 2, 3, A3 is denoted by 1, 3, A4 is denoted 1, 2, 3 and A5 is 1, 3, 2. Now here is a table where we have shown the properties of this element, some properties of this element. Here we can see that if we combine the identity element, then we take the identity element. If we take 2, 3, if we combine 2, 3 with 1, 2, then we can get 1, 2, 3. So here from this table we can see that if we combine any two element, then we get some element of this list, not other element. The function satisfies some special kind of property, and this property gives the birth of the group theory. Now, for the above discussion, it is clear that combination of any two element of symmetry gives an element of symmetry. This symmetry is called symmetry group or permutation group of A, and it is denoted by S3. Similarly, we can define the permutation group of n elements, and it is denoted by Sn. Group theory was first introduced by Galois. Galois used this term group theory in a technical sense. He wanted to study the roots of a polynomial, and he has shown that the roots of an n degree polynomial where it's an n variable polynomial, if it has some root, then this root satisfies some permutation properties. He gave the definition of a group by using the roots of an polynomial. Actually, this modern definition of a group was first given by both Heinrich Weber, Walter von Dirac in 1882. But it did not gain universal acceptance until 20th century. Okay. So this is some historical notation, some history of group theory.